So we're in the home stretch. We only have this one, as far as big topics go, just this one, although there's a lot of stuff here. And it's because we have to talk a bit about performance and some implementation things. Now, I've said before that this is the kind of course where we can go in so many different directions that it would be nice if it were two courses, because it's like one side being applied things like SQL and insert and create, and the other side being what's happening in the background. So the isolation stuff from last time, and how do we store tables? So we don't want to talk too much about exactly how tables are stored on disk, and again, because we might be stepping on the toes of CSC 360, but also because there's only so much time. But one thing we have to talk about is, at least to some extent, how is it that we can run queries on a database, even if they're incredibly complicated or require access to a huge amount of data, and the database might take a little while, but it's surprisingly fast, even if our data is complicated and varied and there are a huge number of tables and we're doing lots of joins. And so one thing that we're not going to get time for this semester, that usually every semester it's hit or miss whether we have time for it, is the process that the database uses to optimize queries. And so that's very complicated. What it does is it'll take your entire query, even with all the with clauses and other things, and try and rearrange it in a way that allows it to evaluate the query quickly. So that's something that gets covered in higher level courses to some extent. But what I want to talk about, certainly, if we don't have time to talk about the query planning, is at least how does the database efficiently manage all of the different requirements that you have on data. So you might have a huge table. In fact, I'm realizing now that there are slides that talk about this. So here is our VWSN database. So we've got, and I've simplified a couple of things for the sake of not having to worry about date time things. We'll model the observation time as a bunch of ints. Now, you should know by now that, of course, this is convenient as far as talking about it, but it's sort of better to model the date and time as a timestamp, because then we can compute differences with the built-in functions. But suppose that our observations table and our stations tables look like this. And our primary key is observation time and station ID. And then we've got a foreign key as usual. And we know that the database does have some clever way of managing this, because this is a constraint that it enforces. We've already talked about that. This is this database that we've been working with on assignments on assignment 4, the VWSN database, is pretty big. Given that this data system, not necessarily the exact data set that we're working with, but this weather station network has been in service since the early 2000s, I think 2003 or 2004, and it's been recording data from what are now hundreds of weather stations at 5-minute intervals for the last 16 years. And so obviously that's going to be a huge amount of data in their main database, and that is millions of observations per month. This is just emphasizing what I said a minute ago. So first thing, 1 million, the number of observations per month that I just described in this data set, is actually, that wouldn't be considered impressive. Database systems can contain, in some cases, tables that might have trillions of things in them. But certainly, billions of elements is pretty common. And so we need to understand that when you issue a select statement to this database asking for every observation where the temperature was the value 6.72, it can come back and find that pretty quickly. Even though the entire database isn't being stored in memory, it's maybe stored on disk, it could be stored on different disks, it could be stored on different nodes of a cluster on a network, and yet somehow it's able to do this processing really quickly. Just to back up a little bit here, so there's about theoretically millions of observations per month. The data set that we've been working with, which is 1 year of this data, I think it has something like 11 million observations, and that's because we're actually not keeping all of the different observations. It turns out that this data set, the weather station network, you can go to their website and take a look at it, but they're tracking data from more stations than our data set is. Our data set's only using certain stations. And they're not just tracking temperature. They're tracking a variety of other data points. And so we were working with a very stripped down version of it. And I think the observations table in our 1 year data set's got about 11 million entries, 11 million distinct observations. And yet, if I search it by any particular value, so if I ask for all the observations for a given station, all the observations on a given day, all the observations with particular temperatures, the result comes back pretty quickly. And so we want to figure out why that is. What is the database doing? Now, it turns out we'll see that it's not just the database. When I created the data set, I had to add a couple of extra statements to tell the database what I expected to do lots of searches on. And I had to predict, I guess, what people were going to need for assignment 4. And the same is true of the Fairies data set and the IMDb data set. I had to give the database hints what I will likely be searching a lot. But the database had to do something in the background to make that search feasible. So let's take a look at this query here. Let's select every observation from station number 6 and this month and day. And we know that on Postgres we wouldn't just say month equals 1, we do the extract function or something. This query does what's being described. All observations from station 6 on this date, and it's probably the obvious query you would write for this. So my question is, select star from observations and then a where clause. This can be evaluated in the most naive way by just looping over every row in the table and then asking the question posed by the where clause. And if the answer is yes, keep the row. That's the way we understand the where clause to work. What about this version? I select all the rows from station number 6. And I select all the rows from January 9th, and then I take their intersection. So I now have 2 sets of rows, and I take every row that appears in both. Maybe you can see that this is exactly going to produce the same set of result rows as the previous query. These queries are equivalent, and yet, and you can try them out. One of them will probably take a different amount of time. And I've warned against this in previous lectures, but it's a bit dangerous to go around assuming which query is going to be slower because there are lots of factors in play. I would say, if I had to guess, that the majority of people watching this video, hopefully there's more than 0 of you by now, the majority of people watching me do this video probably think this is the, I don't know, I'm doing air quotes here, better query. They would think this looks a little bit, this looks like we're trying our luck. It is equivalent, but it's equivalent in a very academic sense. Yes, sure, we can use this as well, but nobody would actually do that, right? Right? So the problem here is that when we think about the way the database works, we have our own bias as to, I don't know, what's a good query, what's a fast query, and often, this is not just true of databases, it's true of writing C code or C++ or Java or Python. Often we've got these biases and it's very hard to talk us out of them. We just think, this makes more sense. If I had to write the code to evaluate this, it would be faster this way. And this just looks weird. Intersect feels like a slow operation. We shouldn't have to do it. This is computing 2 results and then intersecting them. That seems slow. It seems slow. So we should know better than to assume anything. I would say that there are reasons why either query could be better, it turns out. Odds are, without any extra scaffolding involved, this query likely would be faster on our data set for a lot of reasons. Another thing is that the database system, if you hand it this query, and this query would have been slower, it might notice that and do it the other way. It could optimize it into the best form. So there are a lot of variables there, and of course that's why we shouldn't second guess the compiler or second guess the language or database system that we're working with. The key here is that it's worth considering that we should be allowed to give the database this query or to give the database this query and have the result come back pretty fast. It's not our problem how the database does things internally. The database, if we tell it what we want concisely, and these are both concise ways of saying what we want, it should be able to give us back the result. So largely it isn't our problem how it's optimizing things, but it's worth considering that somehow it's able to do both of these operations relatively quickly. So the question, which query is better, that's actually hard to answer. And really what we're doing there is starting a political debate. It's a question of which one seems to make more sense. I would say that if you come out of an imperative programming background, you probably like this one. Because you would, I don't know, internally, your brain would map this more onto the type of simple loop that you might write if you were doing this. If you come out of maybe a functional programming background, this might not be as alien to you. So let's consider another example before I get to my main point. Let's say I want to find all stations that have at least 1,000 observations between -6 and -5 degrees. So we don't see that very often in Victoria. So -6 and -5. and at least one observation between -6 and -5 between midnight and 1 a.m. on February 1st. Now, the reason that I bring that up is because it maybe is clear that unlike the previous example, you really can't phrase this as a single select statement. You need the intersection here. And so the database has to go and do two different searches. Here, it apparently is doing two searches and then merging them together. But in this other version of the previous query, it was able to do it all in one search. In this example, it has to go do two searches, certainly because it has to, even if we're looking at similar things, and maybe it notices that, the fact that I have to aggregate changes things. It's true that the database might see through this a bit and notice that it should just be going and finding all the rows that have this property and then doing one of two different things with them. So this query here meets the criteria of our previous slide. Should we do anything to it? And again, this is a loaded question. Should we have to modify this query to optimize it? Now, many of you on assignment 4 noticed that, yeah, the database is slow on some queries, and you might have to tweak the way your query is written to make the database run the query quickly. So I can't necessarily get on my high horse and say, well, you should always leave optimization to the database, because there may be, although that's a good ideal situation, the database might not be smart enough to perfectly optimize everything. So the goal ultimately is that we should just be able to write a query that is concise. Anything that does what we want should be a good query for that. And ideally, the most readable query is the best query instead of the query that the database likes the most. But it is unfortunately true that the database can't always optimize everything perfectly, and that we might have to give it some help in some cases. I still don't know whether this is necessarily the best or worst way of doing this, but it might be the case that we have to understand how the database is working with data to better be able to optimize queries or provide it something that it can work with. We hope that its optimizer can take a query like this one that's nice and readable and convert it to whatever form is needed for it to be fast. But maybe it can't always do that perfectly. And so maybe it is useful, even if we're not implementing a database system, to know about how database systems evaluate queries. And as I've said, that could be 3 weeks of the course, but we don't have 3 weeks. So instead, I'm going to focus on the big question, which is if we're searching a big table, what data structures is the database using underneath to facilitate that searching? And also, how do we get around, what is the number one enemy of database speed? And how do we work around it? And it turns out that unlike in a lot of previous settings where your number one enemy is running time, so you assume everything else is secondary and you want to optimize running time or space consumption. You've got a big O of n squared algorithm where n is your input size, and you want to make it a big O of n log n algorithm. And that's certainly a noble task to take up, but it turns out that database systems don't usually have that bottleneck. In most cases, processing time isn't our biggest enemy when we're working with a huge data set. And so this is pointing out that, of course, SQL being a declarative language, the optimizations I as a programmer can perform aren't really the same as they would be in C or Java, where in C or Java, if I think something is happening slowly, I rewrite the algorithm. In SQL, you don't give an algorithm. You give a sequence of transformations. You describe what you want, and the database has to go and figure out how to do it. We don't want to impose, I guess I've gotten ahead of myself a little bit, we don't want to impose a particular style. We want, ideally, for programmers to be allowed to write whatever they want, and they can use their own internal style, if the database gets a query that does the task, it should be able to execute it quickly. But on the other hand, you might notice that even for a simple search operation, we could write just, gratuitously complicated queries to do that operation. And I suppose it's reasonable that we have to compromise a bit on this. So what we want is, if I design a database well, and I have a well-designed DBMS with an optimizing query processor, then if I hand it any query that's within reason, attempts to, relatively short and does solve the problem, it should be able to evaluate it quickly and optimize it well. As I mentioned earlier, I guess the slide should have been way earlier for this. This might notice that although we certainly have to do two operations, one of them is aggregating, one of them isn't, both of them seem to like all the rows where temperature is between -6 and -5. If the database could figure this out, maybe it could pre-cache those rows and then just go and use the cached version to evaluate each subquery. And so we need to talk a bit about how it does this. And we also have to talk about, at the very end of this, I want to talk about I guess how you can give a hint to the database system about how you intend to use your table. So we can create something called an index on a table that tells the database system to optimize searches in a particular way because you expect to do a lot of queries that will search this. So I want to talk about data structures that are used to facilitate that. It says here the next lecture will cover the mechanics of query evaluation. I think at this point we're likely going to run out of time and not have a chance to talk about that in great detail. Certainly I don't expect that to be on exam, covered by the last exam. So the question then is, how should we store this table? Ultimately, before we can talk about how do we optimize queries, how do we store this table? It's massive. It has to go on disk. And when I say massive, I actually mean, in our case, our VWSN 1-year database, it isn't really that big. It's only about 500 megabytes, which is massive by the standards of what you might be working with in CSC 225, but it's not really that big in the grand scheme of things, especially as far as databases are concerned. So suppose that I want to store the table in such a way that I can optimize searches where I'm asking for all rows with a particular station ID. So I might say, give me all observations for station ID 6. That's a lookup operation. I've got this big table, and I'm storing it, and it's got these values in each row for station ID. I want to look up rows by their station ID. So what I could do is I could store the table in sorted order, and I could use binary search. As you know, if you want some storage mechanism that facilitates very fast searching, storing things in sorted order allows you to use binary search, which is log in. But the problem there is that if I'm searching by just station ID, the row is more than just a station ID. And so even if I've got a pretty small number of records, there is a lot of space being taken up by this table for things other than station ID. So I might actually have to jump all over the place to actually look at every row that I need, because they could be pretty far apart in memory because they're pretty big. Unlike if I just had a row of station ID values, if I have 1,000 rows, I could expect that, or if I have 1,000 elements and each of them is just a station ID, I can expect that you can store that in an array of size 1,000. But if each row is, I don't know, 50 bytes in size, then 1,000 of those is 50,000 bytes. And so even if I'm just looking at station ID, I have to consider the amount of space being taken up by all of my other pieces of information in each row. And then there's this problem, which is, I think, a much bigger issue. The space problem we'll get to in a minute. But okay, I want to search by station ID. I want to be able to pull out all the rows for a particular station conveniently. So I sort the entire table by station ID. That's great. I can use binary search. But what if I also want to quickly search based on temperature or based on date? What do? I can only sort the table by one thing. If I want to use binary search and the table is sorted by what I'm searching, then I'm good. But what if I want to search on different possible criteria? Station ID, maybe date, maybe temperature, maybe the combination of date and temperature. I can't sort the table by more than one attribute. And so I need some way of allowing fast searching of multiple things. Consider in the IMDb database all the different things you're searching for in the queries you've written. You're not just searching for title ID. You're often searching for title ID, but not just that. And so we need to make it so that tables can be efficiently searched by multiple things. And then there's the last thing, which is great. If you have your table in sorted order, that's great for doing binary search. But what if you want to add a row? Your table has billions of things in it, and you want to add a row, and it's in sorted order. That's going to be pretty ugly. And so, of course, there are more constraints than just how do I search by station ID. This is a multivariable optimization problem, and it gets even worse when we think about the fact that the table is probably going to be stored on disk. So here are the requirements we probably should be thinking about. We have a table, it's too big to fit in memory. I might have a server with 64 gigabytes of memory, but unfortunately the table could be a terabyte in size. No matter how big the server's memory is, the table is very likely going to eventually be bigger. So that means that at any given time, most of the table is kept on disk. And I'm going to come back to that in a minute. So if we ignore the disk problem for now, when I insert into the table, I should assume that generally I'm writing tables that I could be inserting into constantly. If we're representing the database of all that weather data, every 5 minutes hundreds of new observations are coming in. So it doesn't matter how often I'm doing searching. I should also assume that I'm constantly inserting records. Given a particular station number and date, I want to quickly find any rows with that station number and date, if it exists. We should be careful. This is implying there's only one of them. There could be more than one of them with a particular station number and date, but there could also be zero. If I give you a range of station numbers, dates, or temperatures, I also want to be able to locate all of the records that fall in that range. So I might want to say, give me all observations from between February 1st and February 15th. That's a valid request. That's a range query. I should also be able to do that quickly. So not just straight up lookups, but also being able to find all things whose value falls in a particular range, even if it's a continuous range. So give me all observations whose temperature was between 6 and 6.5 degrees. I think all of these latter three constraints, I think, are quite reasonable for the weather station database, for the general purpose one, not just the one that we're working with, but actually storing weather observations. The issue here is that if I just consider the last three, maybe I can devise a data structure that works for one of them. Right? So for example, if I'm only worrying about station ID, then I could sort the whole table by station ID. But that screws up insertion. If I'm worried about this range query on, I don't know, station numbers, dates, or temperatures, maybe I can work out a data structure for that, but it may not be as easy, again, to do this or to do this. And so I can solve one problem, but I can't necessarily solve all of them with one data structure. And even if I use a combination of data structures, they might fight with each other. And then there's the elephant in the room. There's this problem. So the issue with this is that if I'm storing my table on disk, I have a new enemy. I don't want a search of a table stored in memory to take too long. I mean, I don't. Obviously, I'm optimizing to do fast searching of my table. I want to reduce processing time or something like that. I want to do it in log n time. But it turns out that I don't care about my running time anymore if my table is stored on disk, because my number one enemy is the time it takes me to read something from disk. And I'll in a minute apologize for using the word disk in 2020, because obviously we may not have physical disks anymore. We might have solid state drives. I'm just stuck on the old terminology. The typical speed of a disk, even a really fast SSD, is way slower than the possible bandwidth of a processor. I could be running millions of operations on my CPU in the time it takes me to to receive 1 byte of data I requested from disk. And as a result, there is an order of magnitude difference between the time it takes me to grab stuff from disk and the time it takes me to do some algorithm with what I get. And therefore, it turns out all we care about, literally all we care about, if we have to worry about this problem up here, is how do we do this thing fast? How do we avoid going to disk? And so there are lots of reasons why disks can be slow. It turns out that there are sort of two issues. There's latency and there's throughput. If I ask my disk to give me the piece of information at a particular location, it has to receive my request, go get that information, and send it back to me. And because if I'm running on the CPU and the disk is running somewhere else, there is some time it takes for those requests to go across the bus and then come back. There's also time it takes the disk to actually do what I'm asking. It turns out that as a result, it's usually faster if I read a large block of the disk at once. I can say to the disk, send me the 2 megabytes starting at this position. And the disk then, once it gets my request, streams all of those bytes back to me. I don't have to make a second request to get the second byte. So what we want to avoid is random access to the disk. I would rather read one contiguous region, maybe enough that fits in memory, so a few megabytes at a time, and then pick through it in memory. I don't want to have to ask the disk to do too much work. And if I can avoid it, I want to avoid doing any disk access. I want any disk I/O to be avoided. Because a single disk I/O operation, reading a megabyte from disk, takes so long compared to everything else, if we have to do disk I/O, we pretty much think about the operation in terms of how many disk I/Os do we need. So let's talk a bit about that word disk. So you might be familiar, I mean you should be, from CSC 230 with this idea that computers have a memory hierarchy. At any given time, we like to contextualize what we are running on the machine. If I'm thinking of me being the computer program, I always feel like I'm in the CPU. So at any given moment, the easiest memory for me to access are the contents of my registers. And a particular machine might have anywhere between 4 and 128 general purpose registers. And so that's the fastest fastest way I can access data. There's also main memory, and we like to, in most contexts, think about there just being registers in main memory. But there's also usually a cache defined in hardware, or several layers of cache that can moderate access to main memory. So if I request something from memory that I've seen recently, maybe it's in the cache, and that should be transparent to me. I think I'm loading from memory. It doesn't matter that maybe there's a cache in the middle that can handle that request more quickly. That's all stuff from 230, and we're certainly not going to belabor stuff like cache accessing or cache access timing or whatever in this course, but we should be aware that most of the work that we've done up until this point, maybe in your whole degree, has happened at here or above. We certainly know about files on disk. Obviously, we know that you can just save files to disk and you can load files from disk. But as far as writing efficient algorithms and data structures, we've been thinking of, assuming everything is being stored in memory, or that if it's on disk, load it all into memory and then work with it. There's never been this notion of, hey, your data's on disk and there's so much of it you can't bring it all into memory. You're going to have to keep swapping it in and out of memory as you go. And so we often optimize different levels of this hierarchy. So for example, when, the highly optimized high-performance computing libraries used for linear algebra often spend huge amounts of development time working on making sure we never have to go to main memory. So designing special implementations for each type of processor to optimize the chance that a piece of data is in the cache at any given moment. And that's useful if you're doing high-performance linear algebra where you're assuming everything's happening in memory or above. The problem is, in a database system, sure, you want to benefit from cache, but you pretty much need to be keeping things on disk. So for the very basic, for performance reasons, that's because obviously your disk is the only thing big enough to store your table. So even if, you wanted to do everything in memory, you couldn't. The disk, you need to store stuff in disk because you don't have enough memory. So if you're entirely performance oriented, you still have to go to disk because there's simply not enough space in memory. But there are bigger problems. And one of them is, how do we implement an ACID-compliant database if we don't use disk? So if multiple threads or multiple machines on a cluster or multiple processors can use the same table at the same time concurrently, it needs to be somewhere that's common ground. A cache might not be shared among multiple processors. In multi-processor systems, often a cache is unique to a single core or shared between 2 cores or 4 cores or something. And main memory usually is common to the entire machine, but may not be common to all of the machines using the piece of data. So there are also concurrency-related reasons why we would need to use disk. And then there's also durability related reasons. So we talked about atomicity, consistency, and isolation. That's 3 of the 4 letters of the ACID framework. There's also durability, which is that I would like it to be the case that if I insert a row into a table and I commit the transaction, that modification is permanent. And if the power goes out or something, that modification is still there when the power comes back on. I can't always achieve that, but I need some mechanism to keep the database consistent, ideally keeping stuff somewhere that it's going to be permanent. So I need to have it on disk eventually in any case. As far as I mentioned in the atomicity lecture, as far as durability is concerned, we don't generally talk about it too much in 370 these days because it would require too much knowledge of file systems, and 360 talks about that. So just to be clear, I use the word disk, maybe you use the word disk. The term disk traditionally meant a hard disk, which was a spinning glass platter that would spin around at 5,400 or 7,200 RPM, or maybe 10,000 RPM. And the glass platter is covered with sort of a magnetic powder, for lack of a better term, tiny magnetic grains that then are encoded into a magnetic state by a read head that goes across the surface of the disk, and their persistent magnetic state is used to represent 0 or 1, which is how data is stored on disk. And the disk spins, and we therefore have to work out, based on its rotation speed and how far the read head has to travel to find a piece of data, how long it takes to get data. I remember taking 370 and having to do that, and thinking to myself, hey, this is, I don't know, that was the 2010 or something like that. I was thinking, hey, in 2010, this seems a bit dated, talking about a disk that spins around. So I'm not going to continue that tradition. In 2020, we're not going to worry about how long it takes the read head on a hard disk to find a piece of data, because we know that there are plenty of hard drives that we use, like solid-state drives, that are not disk-based. They're actually digital logic based, so flash memory or something similar to that. So we're not going to worry about the exact timing details of how a disk is structured. The issue basically basically, though, is that ultimately there's something below memory, and it's disk or it's network or it's cloud storage or whatever, and it's slow. It's really, really slow. It has relatively low throughput compared to a CPU or memory, but also really high latency. It takes a very long time to get data back from this secondary storage. I'm going to keep saying disk because, I mean, you can't teach an old dog new tricks, I guess. But of course, I mean secondary storage. Usually, though, I mean a hard drive, whether that's a disk-based one or something else. So yeah, this is my disclaimer about how 370 in the past, I don't know how recently they've done this, would spend all this time talking about rotation speed and seek time, and those are interesting things to think about. But because many of us are using solid-state drives, I think the machine I'm recording this on is a solid-state drive, I don't know if we want to spend too much of our valuable time in this course talking about that. So we're going to make some basic assumptions, just like how in isolation we didn't want to talk about p-threads or something. We wanted to talk about concurrency at a higher level conceptually. We're going to do the same thing for disk storage in 370. Let's make these assumptions for our proverbial disk, whatever it is, network storage, an actual disk, or a solid-state drive. First, random access, which is I send a request to the disk saying, give me the sequence of bytes starting at address 5079. That's random access. I ask it for the bytes from an arbitrary location. It's possible the disk can service a request for any location, but extremely inefficient, usually because of latency. I have to send the request to the disk has to receive it, go find me the thing, and then send it back. So asking for a single byte is very inefficient. In general, asking for sending in any request is high overhead. So I want to minimize the number of requests I send. So that brings us to point number 2. We'll divide the disk into blocks of a fixed size. And the blocks could be of a size 16K or 1 megabyte. I think our Postgres servers that we've been using use a block size of 8K by default. And maybe I should have tuned that and set it a bit higher or something. So we divide our disk into blocks, and if we want a piece of data from inside of a particular block, we read the entire block. And the idea there is that every request I make to the disk is slow. And so I'd rather avoid making too many requests. So what I'll do is only ever read disk data one block at a time. And I'll assume that my blocks are small enough that I can fit a few of them into main memory. So for example, if my blocks are 1 megabyte, I could read a million of them into main memory with no big deal. I couldn't read all of them because there might be more than fit in main memory. But I want to be able to batch my operations to some extent. And so in any case, though, even if I'm reading the data one block at a time, reading that block takes an order of magnitude longer than reading main memory. So disk I/O is a big deal, and I really want to avoid it. And I want to just circle back and emphasize, why are we reading blocks and not single bytes? Why is it so much faster to read 1 megabyte at a time versus 1 byte? And the answer is, if you only need literally 1 byte and you're never going to need a second byte, then it's not. But usually, if we're reading data, we want more than 1 byte. And if I send a special request for each byte, I am stuck with that transit time of sending the request, the disk receives it, and the disk sends back the data. If instead I tell the disk, send me the 1 megabyte of data beginning at this address, the disk has to receive my request and then begin sending me back the data. But all the data comes back in a row. So once the first byte arrives, the next byte will arrive really quickly. That's the idea. And so I can benefit from the higher throughput and lower latency by sending one big request instead of several small ones. So here are my optimization goals. First, if I'm reading things one block at a time, then of course I want to try and make sure that if I want more than 1 byte worth of data, it's sort of nearby, because that way it's likely to be in the same block. If I need 3 pieces of data and they all happen to fall inside the same block, I can read all 3 of them by doing one disk access. I just read 1 block. And just to be clear, for the rest of these slides, I'm going to keep counting things like disk IOs or disk reads. Whenever I talk about a disk IO or a disk read operation, I'm talking about 1 block. So disk read would be a single block read from disk. So if I have locality, if I've got my items, related pieces of data tend to be close together on disk, then it's more likely that one or a small number of block reads will get me all the data I want. Okay, so that's one thing. The second thing, which is the biggest departure, is because disk I/O is so onerous, I no longer care about the exact running time of my algorithms, assuming basic stuff like that my algorithms are, for example, no worse than n squared. I don't necessarily care if an n log n algorithm exists, if it's going to require me to read the whole disk, if there's an n squared algorithm that requires me to read one block. And so we're going to spend the rest of this lecture not even worrying too much about this problem, about the whether we have an n log n search algorithm. Instead, I'm going to care about the number of disk blocks read or written. That's all I'm going to worry about, because it's so slow to read or write from disk that the slowdown of extra processing time wouldn't really be observable by comparison. So my biggest blocking factor is disk I/O, and that's all I need to worry about. I certainly still want efficient algorithms, but ultimately, if I have to compromise on something, I want to compromise on saving disk I/O, maybe at the expense of processing time, up to a reasonable limit. I don't want exponential time algorithms, but I'd maybe rather have an n squared algorithm that reads one disk block than an n log n algorithm that reads every disk block. So since disk blocks tend to be big, obviously we can expect that if rows are relatively small, a database can probably store multiple rows in one block on disk. Normally, the database will break things up such that a particular disk block only contains rows from one table, unless there are extenuating circumstances. So, for example, if I have several tables and they get divided up into blocks, I would usually have an arrangement sort of like this. So here's T1, here's T1, here's T1, here's T1, and then and maybe T1 ends here, and this is just empty. And then there's T2, and then there's T2. So usually the reason I do that is because I want to keep tables in separate things, and also I want to save a bit of empty space in case I want to add new rows or something like that. It's pretty easy, a pretty straightforward arithmetic exercise if I tell you the block size and I tell you the size of each row for you to tell me how many blocks or how many rows go into a block. And we're going to need to do that. We do need to spend some time doing some of these low-level calculations to be able to figure out how many disk IOs I need. I'm going to spend some time talking about that. I'm going to post some notes about the actual arithmetic separately, and I'll also talk about that in the live tutorial things we do on the next couple of Mondays. So there's also this. I'm just going to leave this here. The book, and I think some offerings of this course, spend all sorts of time on this, and I'm a big fan of merge sort, but I tend to feel like we don't need to do the low-level analysis. You've done that in 225. There is a variant of merge sort, a special style of merge sort that's able to, if I have this data set that occupies a whole bunch of blocks, and there are B of these blocks, then there is this special type of merge sort called two-phase multi-way merge sort. You can take a look in the book for how it works exactly. And it can sort a data set so the table takes up all of these blocks, and the table could have lots of rows per block. It can sort the rows of that table using a total of 3B disk IOs. Notice how I don't even point out what its actual asymptotic running time is in terms of the number of rows. All I care about is how many blocks I'm reading or writing. So assuming that I can store 3 blocks in memory at each step, in a total of 3 times B I/O operations, reads and writes combined, I'm able to sort the entire table. And of course, if I'm storing the result back to disk, it ends up taking 4B because I'm actually saving it. But if I want to read the table and sort its rows and output them, so just print them out, so you've used dbeaver to send in a query that sorts an entire table, we can do this with 3B disk I/O operations. So that's one thing. So I'm just leaving that there for later. There's a few reasons why that can be helpful. We'll see them show up in some of the applied stuff that we do, some of the calculations. Let's just talk, though, about the data structure problem. So I would like to search for particular values quickly. So describe a data structure, and this is review. Describe a data structure that allows fast insertion of new records and fast lookups of single elements, not range queries, just single elements. Give me... For example, in this database of students, give me the record for the student with this student number. And then tell me if it's not there, basically. So a fast lookup. And then I want to also quickly insert elements. And you stare at that and you'd say, well, I mean, let's just go through our textbook data structures and see if we can find one. This sounds a lot, fast insertion, fast lookup. It sounds a lot like a hash table or a binary search tree. So we'll start with a hash table. Hash tables are sadly misunderstood. There are a lot of people that love hash tables but don't use them correctly. They just love them. They feel like hash tables are the fastest thing in the world, but they often write slow hash tables because, of course, to actually achieve really fast running time on hash tables, you have to have a lot of constraints that many people who write code with hash tables don't bother to enforce. So if the maximum size of your data, I'm going to say relation, just because we're going to talk about hash tables. If the maximum size of the relation is known in advance, a tuned, so a well-designed hashing scheme is a great choice. Because if you're not doing a range query, if I don't care about adjacent elements, I just want the one row that has this property, then a hash table is great because if we tweak all the parameters, the expected case lookup and insertion time is constant. The problem with that, of course, is that if you actually want to get constant time, expected case, you have to enforce a bunch of things. One, you need a very good hash function, which is not always easy to design. You also need to make sure that a certain amount of the hash table is empty if you're using an open addressing scheme, because otherwise your probing sequence might contain big O(n) things. If you use a chaining scheme, which will... I'll talk about in a minute. A chaining scheme for that can have disk implications. But in any case, if my hash table becomes too full, if there's not enough empty space, I have to rehash everything. That's linear time, which of course would require me to maybe read and write every block of my table on disk. That's bad news. And hash tables, and as I mentioned a minute ago, hash tables have this compromise of how do you deal with collisions? So one option, the so-called open addressing scheme, would be every element is actually stored physically in the hash table. So I put an element, it goes there. I put another element, it ends up here. I put a third element, it ends up here. And now I want to insert an element W. And W is supposed to go into this bucket here. But it has to go in the table somewhere, and this bucket is full. So an open addressing scheme would say, go find another bucket to use. An easy one would be just find the next available one, put W there. And if there aren't if we don't guarantee that there's a certain amount of empty space in this table, then when I go to search for an element, I might always be wading through existing elements. If I go searching for, let's say, so I put W there. If I go searching for W in this table, I would say, okay, W is supposed to go into this bucket, but it's not there. But it might be in the table. Maybe I put it somewhere else. So I'll keep looking at adjacent buckets until I see an empty one, and then I'll stop. So the sooner I find an empty one, the sooner I can stop. If I don't, therefore, keep a certain amount of the table empty, the hash table search time can plummet. So that means I have to make sure the table always has a certain amount of empty space, and if it doesn't, I have to resize it. Okay, so another option would be to do what's called chaining, which is if every bucket is actually just the beginning of a linked list. And if two things go in the same bucket, they just go in the same list. The problem with that, and that guarantees constant time insertion, the problem with that is that whenever you have a linked list, you're probably walking all over memory because the individual nodes of the linked list could be anywhere. You could have to bounce back and forth between various places. That might mean reading a lot of blocks from disk. Whereas if I have a hash table that's split up over multiple blocks, so to go back to my example from a minute ago, if I have this big table, maybe it gets divided up with this is block 1, and then this is block 2, and then this is block 3. And so if I have multiple things I have to look at, if I end up looking at multiple buckets inside the hash table, they're probably inside the same block. With a linked list, they could be in all different blocks. A list of 3 things could have each node in a different block, so I do 3 block reads. So memory locality is a big deal, and it turns out that hash table has to compromise there. So if I use chaining, I don't get memory locality. And the opposite of memory locality is memory fragmentation, and that can lead to a huge amount of random access. And we'll see in our discussion and the calculations we do about this on the assignment and on the next exam, and in those tutorials, the live tutorials, that actually is a big deal. We do end up seeing a few cases where even if we have good data structures, if we're not careful about how we search, we end up using a huge amount of disk read operations. So another option, if hash tables aren't your taste, is a binary search tree. And we know from 225 and 226 that there are these binary search trees that are so-called self-balancing trees, an example being a red-black tree or an AVL tree. I guess it depends on who you took 226 with, which one you saw. And these binary search trees allow you to insert or look up values in log n time. They're also nice because a binary search tree facilitates what are called range queries. I guess I'll need a binary search tree here. so there's 6 and 3, and then there's 1, and there's 2, and there's 4. This isn't perfectly balanced, but it would meet the criteria, I think, to be AVL. So then there's 10, and there's 9, and then there's so a range query is for me to ask stuff like, could you please list all of the numbers between the number, let's say 5 and 11 inclusive. So I'm saying, give me everything between 5 less than or equal to 11. So what we would do is find where in this table 5 would go, and it would go sort of down here. And then we do an in-order traversal starting there and list everything we see until we see an 11. So 6, 9, 10, 11. And it turns out, you may know that binary tree traversals are big O(n). So it turns out that if I can find 5 and I can find 11, then I just do a traversal between them, which is really fast. And so it turns out it has this time, although again, this is CPU time. It's not with things in main memory. It's not necessarily disk reads. The problem with binary search trees is that we normally implement binary search trees with you could call it a pointer-based, a linked-based representation. I make a node, and it has a pointer to its left child and a pointer to its right child. But in memory, they can be just about anywhere. The pointer tells us where in memory to go, and we're used to memory access being cheap. We're used to having everything in main memory, where if one node is at address 1000 and one node is at address 1,000,000, no big deal. You just go to a different address. You've maybe seen in 230 that there are cases where we can optimize that a bit for cache purposes, but it's not nearly as bad as it is when we have disk accesses. If all 3 of these nodes are in different disk blocks, then doing a traversal of this tree requires me to read 3 blocks from disk, and I may be able to find a way of structuring my data so it only requires 1 block read. So I'll give an example with this diagram. Here's a binary search tree, and actually maybe now I can illustrate a range query better. Suppose I ask for everything in the range 7, this is an inclusive range, 7 up to 17. So I do I could view this in a couple of ways. I would probably do first a find operation. I would go searching for 7. So I go, okay, 7 is less than 10, greater than 3, greater than 5, greater than 6. Okay, but 7's not there, but here's where 7 would go if it were in the table. Okay, so then I start at that position, that imaginary position, and I do an in-order traversal of the tree starting there. So I hit 10, so I get 10, 12, 15, and then I get to 17, and I say that's my upper bound, so I stop. And it turns out that traversal takes, in aggregate, big O(n) time. Or big O, the size of the range. Not n could be the size of the table. So the links between these nodes, though, are pointers. And that means that although the tree looks like this when I draw a diagram of it, it doesn't necessarily look like this in memory. We like to think about the tree looking sort of like binary search, where, this is what we would do. If we did binary search on this array, we would get this pattern. So if I say, tell me if the number 5 is in the array, well, we look at the middle and we say, well, the number 5 is less than this. So remove the top half and then cut the remainder in half and go to the middle. So we go, let's say here, we round down. Okay, 3 is too small. Now look at halfway between 3 and 10 and we end up getting 5. We like to think of a binary search tree as a representation of binary search, as taking an array that we're doing binary search on and turning it into a tree. We just take this array and then lift each node up and turn it into a pointer like this. The problem is that in memory it could look like this. The nodes could just be anywhere. And they're tied together by means of pointers. There's no real order to them. So 10 could be here, 3 could be way over here, and then 1 could be here. And there could be millions of elements of memory between them. And that means if I want to do something really basic, so let's say I want to walk down the tree, let's say 10 to 3 to 5 to 6. So I want to do just that basic traversal to find the element 6. Well, it could be that I first go, the blocks might be divided up like this. So I'm going 10, 3, 5, 6. I have to read this block to get 10. There's B1. I then have to go read this block to get 3. If I'm lucky, B1 is still in main memory and I don't have to read it again. But I might not be. If the tree has lots of levels, this might be out of memory and I might have to read it again. So I've already done at least 2 block reads and then a 3rd block read. Even though the set of values I actually have, the nodes, there's only 10 or whatever nodes in the tree. I shouldn't need to read entire blocks off of disk. And so a binary search tree has some disadvantages there. And the problem is we may not be able to avoid that. If we use a search tree representation, we may have this problem no matter what. But it's really severe with a binary search tree just because of how many independent nodes there are. If I have n elements, I'm going to have n independent nodes. And in the absolute worst case, I could have to do n block read operations to do something simple like list the contents of the table in sorted order. And so if I'm not careful and I'm storing this on disk, and remember that disk access is our main enemy here, then I could end up having to read a huge number of blocks, even if theoretically the binary search tree is really fast for things like lookup. And just to be clear about why that's significant, if we think about this in terms of, let's see, what do we have here? 1, 2, 3, 4. We've got 9 elements in this tree. I'll bet, no matter what table this is referring to, I could probably fit the entire table into 1 or 2 or 3 disk blocks. But if I have to wander around and read 2 or 3 things just to look something up, it probably would have been faster for me to just read the table from disk and do linear search, just row by row asking a question. If I'm searching for the value 6, I read block 1, I read block 2, I read 1 more block. I read 3 blocks to find the value 6. I might have just been able to go read every element of the table and ask each row, are you the value 6? In fewer block reads. So one idea would be to organize the tree so that each node of the tree is stored in, like to group all of the nodes of the tree into blocks. And I could modify my data structure to make that a little bit easier. So I could use something, for example, a 2-3 tree. So you will recall from CSC 226 or 225, those of you that took 225 with me, there was a moment where I would have said, this is a 2-3 tree. You don't think you need this now, but you're going to thank me one day. And today, you probably will not thank me for that. You just wish I didn't necessarily bring that up. You didn't want to have to do that on a 225 exam. A binary search tree's disadvantages maybe are just that there are too many independent nodes. So maybe what I can do is try and find a way to make fewer of them. And one way of doing that would be to use what's called a 2-3 tree. And we'll see that what we really want is a development of a 2-3 tree. The idea behind a 2-3 tree is that there are fewer nodes because you're allowed to cram more than one value into a node at a time. And so the search operation is very similar to what would be going on in a binary search tree, except that you can have nodes that have, actually the next slide is going to talk about this. Well, I'll draw it anyway. You can have nodes which have more than 2 keys in them. So in this case, this is all the stuff that's less than A. This is all the stuff that's greater than or equal to A and less than B. And over here is all the stuff that's greater than or equal to B. And so a node that has 2 keys will have 3 children. A node that only has 1 key will have 2 children, just like a binary search tree. So the way that I would search the tree is the same as a binary search tree. I start at the root and I work my way downwards. And so the advantage of this is because I can cram more than one thing into a node, I'll probably have fewer nodes overall. So let's take a look at this. This is apparently review, so I'm going to go through this part quickly. The thing we need for 370 is coming up next. Insert this sequence of values into an empty 2-3 tree. So the protocol for insertion into a 2-3 tree is a little bit different than it would be for a regular binary search tree. And what we do in a binary search tree is typically go find where the node would go and then chain on an extra node below it. So we have something like this. We have a tree, and if I want to insert a new node, I figure out where the node would go in the tree. So I'd say, okay, let's say it would go here. And then I just insert that node. I stick a new node at the lowest level. To insert into a 2-3 tree, we don't do this. It turns out that 2-3 trees only grow in terms of adding a new level upwards. And I'll try and explain that in the next minute or so. Okay, so we insert the value 31. The tree was empty, so we create a new root. Now, by default, whenever we add a new node, we try to cram it in to an existing, whenever we add a new key, we try to cram it into an existing node. Every node in a 2-3 tree can contain up to 2 keys. So we want to add the next element, we just jam it into the node that contains 31. Now the node contains 2 keys. That is as big as it can get. The next node we want to add is 15. So we again try the same thing. We try to cram in the value 15 to the existing node, but we can't do that. The node can only contain 2 keys, and we tried to cram in 3. So here's what happens. I like to view this as we try and cram in a 3rd key, and the node gets too big and sort of explodes into 3 pieces. And so what happens is we take whatever node we end up with. Here, 15 falls in the middle. But in any case, we add our 3rd element to our node. We put the elements in order. The middle element goes upwards, and the other 2 elements go outwards. And so we end up getting 15 goes up, and then 4 goes to the left, and 31 goes to the right. The node explodes into 3 pieces. And that is the way that we end up getting extra levels in the tree. So we do this, 15, the node is too full, so we split it, it splits into this. And in general, that only happens if the node has been overfilled. If there's space in the node, we always add a new key to the existing node. And in this case, exploding this node upwards, 15 ends up becoming the new root of the tree. So the tree did grow by 1 level. We add a 9. The 9 ends up getting crammed into the node with a 4. We try and add a 2. The 2 gets crammed into the node with the 4 and the 9, which means the 4 goes up and the 2 goes out, and so does the 9. So the 4 gets sent upwards. What does that mean? Do we split? Do we do this? This is where I'd ask people in the audience. Well, no. The 4 gets sent upwards. So where's upwards? Well, hey, it's up here. We just cram, and then we try and put the 4 into this node. We cram the 4 into the node with the 15. And when the 9 got sent outwards and the 2 got sent outwards, they now become the children. So this is, the 2 is less than 4 and the 9 is between 4 and 15. So now these become the two of the 3 children of this 2-key node. And then we insert the value 6. It joins the node with the 9. We try to insert the value 5. The node is too full. So the 6 gets sent upwards, and the 5 and 9 get sent side to side, and of course that creates a problem. The 6 got sent upwards, but now this node is too full, and of course it also has too many children, so we need to do something else. So we split again. We resolve the problem by sending the 6 upwards, the 4 goes outwards, and it takes with it everything that is on the left here. The 15 gets sent in the other direction, and it takes the other half with it. And so we get this. And notice that because of the way we're doing this splitting, the only time the tree ever grows in terms of height is when the root splits. If the root gets too full and explodes, then the tree grows by 1. It otherwise doesn't grow. Every other case we've had, we've just kept pushing stuff upwards and there's been space. Because of this, when the root does explode upwards and the tree gets taller, the tree is actually always guaranteed to be full. So what full means is there's never a gap somewhere. Every level is always filled all the way up. There's always a node in every position. And that's useful because it makes it actually really easy, not that we care about it here, but it makes it easy to prove things like that the search time is log n. Unlike a arbitrary binary search tree where the tree can end up looking really stringy, so you can actually, a binary search tree, if you're unlucky, as you may know, if it's not a self-balancing binary search tree, you can get a situation like this where the tree just sort of looks like a linked list. It ends up having a huge amount of gaps on every level. There's lots of nodes that aren't used up. And so the height of the tree is way more than log n, so search time takes big O n. The advantage of a 2-3 tree is because of the method we're using to grow the tree, we never have that problem. Every level is always occupied, so the height is always big O of log n. So the search operation, which starts at the top and works downwards, always takes log n time. So we're getting a lot of the same benefits of a self-balancing binary search tree here. You may also remember that that's no coincidence because a red-black tree, one of the types of self-balancing trees you've probably seen, a red-black tree actually is a representation of a 2-3 tree. Okay, so we add the value 2, it gets inserted into the node, the value 3 gets inserted into the node containing 2, and that was the entire set of insertions. So it turns out that this actually has the same find and insert guarantee that self-balancing binary search trees do. So the height is always log n and find always requires log n time. The advantage of this is that because there might be more than one thing in a node, we might save some disk access. If every node in the worst case has to be loaded from a separate block on disk, and we have it arranged like this, maybe we've saved some disk access. But that's not enough. We've seen in this tree a lot of nodes just have one thing in them, and we're not getting that benefit very often. And more importantly, hey, if we can cram 2 elements into a node, why can't we cram 5 elements into a node? And we can. It turns out that 2-3 trees are a basic case of something called a B tree. And in a B tree, so in a 2-3 tree, we've got 2 elements per node. In a B tree, we just decide, we choose in advance a fixed value, k, and we decide that we can have k elements per node. And just like a 2-3 tree, in a B tree, even if you have 5 elements per node, as long as that's a constant value, the find and insert operations are still log n. Now, because in a B tree, I could decide that there are 100 elements per node instead of 2, I could reduce the number of nodes significantly. In fact, what I could do is I could observe that if my disk block is big enough to store a node with, I don't know, 1,000 things, maybe I should just make my nodes have size 1,000. And so because of this, I can get a compromise where I still get log n search time. I have to do a bit more work because, of course, if my node has lots of different values like x, y, z, and w, and then that means if it has 4 values, it could have 5 subtrees, one for each possibility, less than x, between x and y, between y and z, between z and w, and greater than w. Because of that, the bigger the node is, the more keys it has, the longer it takes me to process each level. I have to figure out, if I'm searching for a specific thing, which direction do I go? But on the other hand, that's something the CPU can do. And we know that the CPU time isn't the problem here. It's disk access time. So we can use this to make a compromise. A little bit more time to do the search inside of each node, but still a log n search time. And we avoid doing as many block reads because there are fewer nodes in existence. There's also this problem of a range query. So you might notice if we do an in-order traversal of a tree, so if I say, give me all the keys between 3 and 9, so what we're doing is we go find 3, okay, there's 3, and then we do an in-order traversal, which amounts to this. Usually you implement a traversal recursively, but it amounts to this. 3, then go up a level, get 4, then get 5, then go up 2 levels and get 6, then get 9, then get 15. Notice how if we draw that out, we were walking all over the place in memory here. And that's a lot of block reads. We would really rather not do that. We would really rather it be the case that an in-order traversal of the tree starting at a given point uses very few block reads. And so we need a way of remedying that as well. And we have this variant of B trees called a B plus tree, which is a slight modification of the traditional B tree to also allow easy traversal without too many block reads. The database systems book does say B plus tree sometimes, but it also just calls it a B tree. And that's not really a big deal for us because in this course we only care about B plus trees. I'm going to keep trying to say B plus tree because I have standards, I guess, but they are different. A B tree and a B plus tree are different things. In this course, what we are working with will be exclusively, now that this example is over, B plus trees. So when you see B tree in the database systems book, they mean B plus tree, as far as I can tell. So here is an example of a simple B plus tree node. A B plus tree node can have any number of keys. So I'll use the number q here. In this example, q equals 3. There are 3 keys per node. If there are 3 keys per node, it means that there have to be 4 pointers to child nodes. Because there are 4, if you look at any given element that could exist, it could be in 4 states. It could be less than A. It could be, hold on a minute, less than or equal to A, so that's a big deal. We'll see why in a minute. Any number between A and B, including A, goes down here. Any number between B and C, including B, goes down here. And any value that is greater than or equal to C, I guess this should actually be a straight up less than sign. Sorry about that. Any number greater than or equal to C goes over here. So there are, when you have q keys per node, you have q plus 1 pointers to child nodes. When you're searching, if I'm looking for a value, I would just choose which pointer to follow based on where the value was. If the value I'm looking at is between B and C, then I would go down here. and I would continue my traversal. And because the number of elements in the node is fixed, even if there are 100 elements, I may have to compare my value against all of them or whatever, but that would still be constant time because it's a fixed value. And more importantly, again, processing time isn't the big deal here. Now, when I get down to the leaves, and that's what's so important about this arrangement, it turns out that to avoid our range query problem, we will actually have a special status given to leaves versus internal nodes. In a typical binary search tree, the key 4 lives inside this internal node. That's the only place you can find the value 4. It lives inside an internal node, and the value 6 lives inside this. But we just saw that we don't want that because we don't want to have to keep climbing up and down the tree to do a range query. In a B plus tree, we remedy that by having every node appear, every key, sorry, I keep saying node, every key must appear in a leaf. It could appear somewhere else too. So a key might appear up here because we need to know, does the root represent 6? Because that means, less than 6 goes this way, greater than 6 goes this way. A key can appear above a leaf, but every key must appear in some leaf. So 4 in this case would probably get crammed down here with 5, for example. The advantage of that is that if every key appears in one leaf, so I'll just dummy this up a little bit. Let's try, this is now going to be 4 and 5. This is going to be 9 and 15. This is going to be 6 and 9. And this is going to be 15 and 31. Notice that if every single key is always guaranteed to be in some leaf, if you want to do a range query, you just start at whatever, let's say I wanted to go between 3 and 9. What I would do is only look at the leaves. I start at 3, and then I just walk to the right across all the leaves I can see. And so the advantage of that is it means a range query no longer has to climb up and down. It goes down to the bottom level, and then it walks to the right across all the other leaves that exist. Now you might notice that does require you to keep track of where the next leaf is at each step, which it turns out isn't as big of a deal. So the way that we view a leaf node also contains 3 keys, but unlike an internal node, we don't use the leaf node for navigation. Each key, and remember that every key appears in a leaf, each key has some associated data. So for example, if we're designing a B plus tree for station ID, the data associated with each station ID might be whatever row goes with it. The row contains other data as well. If I'm looking up a student by student number, well, hey, the students table contains, I don't know, the student name, their major or something. The data that I'm talking about here is the row going with this key that we're searching on. And then if I have 3 keys per leaf, there are 4 child pointers that I can use. Well, 3 of the pointers are used to point to the actual data, and the 4th one is used to point to the next leaf, which makes it easy for me to walk through all the leaves in order. And so that's just a convenience because we have these 4 pointers per node. We only need 3 of them for the data. And so to be clear, every single key, unlike in a 2-3 tree or a regular binary search tree, every single key in the tree must appear in a leaf node. Some keys, not all of them, some keys also appear in a higher level of the tree. Oh, no. Oh, okay, so there was a missing closing parentheses here. Maybe that means I'm supposed to, the rest of the slides are in parentheses. And so just to note, because of the way we're doing this, we only want to be able to walk through leaves in forwards order. So notice how there's a pointer to the next leaf, but there's no pointer to the previous one. So because of that, we always use the pointer before each key to refer to the data for that key if we're in a leaf. So that's one thing, but we still have a problem, which is if we're unlucky, we might end up with a tree with this situation happening. Let's look at this, the 2 pointer case. Okay, so I've got 6, I've got 10, and then here's 9. And you might notice if I don't take advantage of this, I could end up with 2 empty elements in every node, and therefore I just am looking at a regular binary search tree. If I'm not careful, I might end up actually having my nodes be pretty much empty at each step, and that's of course not going to be helpful. So we have to add one extra constraint. We call these density constraints, which is if we're going to have multiple keys per node, we need to make sure that some of them at least are getting used. We don't want to have 1 key per node if we've got space for 100. And so the constraints are complicated because if we set constraints that are too strict, it's impossible to represent some trees. So the constraints are as follows. 1, the root must have at least one element, unless the tree is empty, of course. The root is allowed to only have one element in it, though. So there is one exception allowed to the general density rule. The density rules are meant to ensure that you can't have a node that only contains one thing. However, the root gets an exception. The root is allowed to contain only one thing. That is for bootstrapping reasons, because obviously if your tree only has two things in it, then maybe the root will only have one thing. That's life. And then each leaf, if you have q elements per node, so let's say q equals 3 on our previous page here, each leaf must contain at least, in this case, if q equals 3, there would be at least 2 elements per leaf. Every internal node that is not the root must contain q over 2 rounded down. So in this case, if you have 3 things per node, it turns out you could actually have one thing in an internal node, because 3 over 2 is 1.5, which rounded down is 1. So these are the density constraints. And the key is, if a node ends up too empty, if it can't obey the density constraints, that's a sign that you have to collapse the tree down. You have to begin removing nodes from the tree and merging nodes together. So here's a B plus tree. This is a B plus tree using q equals 4, so 4 keys per node. Notice that 187, which appears in the root, also appears down here in a leaf, and 370, which appears in the root, also appears down here in a leaf. Notice also that because each key appears in a leaf somewhere, it's significant to notice which leaf it has to appear in. So because we've decided that every element less than 187 goes down here, if 187 appears in a leaf, it has to appear, well, it's obviously between 187 and 370 inclusive, so it appears down here. And of course, it'll be the first thing in that leaf because it's the bottom end of that range. Notice that because we have these pointers on the lowest level between all the leaves in the tree, if I want to do a range query, like give me all the keys between 17 and 370, all I have to do is find 17, so that start here, go into the root, start here, go down, and then there's 17, and then I just walk along until I hit 370. And of course, I might walk through lots and lots of blocks, but that makes sense because I'm looking at all the rows. I'm finding every row between 17 and 370. And so, so let's just scroll through this. I want to look at an example with a little bit fewer elements. So as far as the density constraints are concerned, it's less exciting if we only have 3 things per node, but you might appreciate that if you have 4 things per node, it would be some difficulty to even draw a B plus tree with 3 or 4 levels. So let's take a look at this this tree with 3 keys per node. Let's talk about insertion and removal. It's not much different than a 2-3 tree. At every step, if we want to insert an element, we figure out where it would go, and then we try and cram it into that node. And it's only if the node is full that we have a problem. And if we have a problem, we have to split the node. So let's insert the value 370. Okay, I want to quickly trace out my process here. So I go down to the root. I say, where is 370 supposed to go in this tree? Okay, well, it's not less than 10. It's not between 10 and 63. It's greater than 63. So I go down here. And then I say, okay, well, this node is obviously full. I mean, I can't cram 370 into this node. So I get down here, I try to insert 370 into this node, but I can't. I have to split the node. So conceptually, I sort of have the same thing like with a 2-3 tree, where I've got 4 things that go into a node that can only hold 3 things. And so what I have to do in this case is split it. Now, unlike a 2-3 tree, I don't just send something upwards. I mean, I might have to move a key upwards at some point or copy a key upwards, but remember that every one of these things has to still be in a leaf when I'm done. So what I really want to do is first come up with what leaves am I left with, and I think what I should do is split it in half. I have 4 elements and I can only fit 3 in a node, so I'll split into 2 leaves. One will contain 63, 79, and then nothing. So it'll have 2 out of 3 positions occupied. And the other one will contain 187, 370, and nothing. Okay, so that means that I now have to have 2 things pointing in from above. And we'll fast forward and take a look at that. So there I've got 6379 and nothing, 187, 370 and nothing. And I have to have 2 things pointing in from above. So 63, the pointer after 63 still points to where it did before, the node that starts with 63. But then, because I have a new leaf, I have to figure out how to link it to its parent. So I bring the first element of the new leaf, the 187 there, I bring that up to the previous level. I send it upwards as I would before. I might have to split the node that happens that I get to up here, but not in this case. And then I store that here, and then I install a pointer to my new leaf at the end of that node. And if we look at it, we can observe it does now obey all the properties we want. So nodes less than 10, between 10 and 63, between 63 and 187, and greater than or equal to 187. And notice that when a leaf is split, unlike a 2-3 tree, the 187 did go up, but it also stayed in the leaf because every node has to appear in a leaf. Every key has to appear in a leaf. A node doesn't appear in a leaf because a leaf is a node. Let's insert the value 13. Now you might notice that the tree is that the bases are loaded here. So you'll maybe forgive me, but obviously on exams you're going to get a lot of trees where you have no choice but to do the splitting operation or whatever. So let's try inserting the value 13, and then we'll notice that there's some not really 225-esque tricks that we can do here. In a course like 225, you're told, here's how insertion works, here's how removal works, you must do it this way on an exam. We might notice there's a little bit of flexibility that crops up here. So insert the value 13. Okay, so how do we start? 13 is between 10 and 63. So we come into the root, we go down here, and then we end up with this problem. So I've got 10, 13, 17, 19. Okay, so I could split it into two leaves. And because obviously it can't contain 13 and all three of those other elements. So what do? Well, I could split into two leaves. So I do this, I perform the split, and then I notice that because I have a second leaf, I have to send 17 up to join these things. So I get 10, 17, 63, and 187 up in this in the level above. And I notice that, of course, you can't put 4 things in a node that only stores 3. So I have to split this node as well. So I think I'll split it the same way I did before. I'll split it into 2 groups of 2. And so because I sent the value 17 upwards, there has to be something pointing down to this. So I have to do this split. And so I do it like this. I split the node as I split into 2 groups. But unlike with a leaf node, I don't actually have to keep the 63 over here. I can send one thing upwards. And in this case, I chose to send the first thing from the right, but I could also have chosen to send the 17 upwards, keep the 63 and 187, and then keep the 10. But I send one thing upwards to represent the new root. And of course, in so doing, the tree grows by 1 level, just like with a 2-3 tree. So you may have noticed that when I split up at the leaf level, I have to keep the element in a leaf. When I split above the leaf level, I might move it over and have 63 and 187. But then when I send something up, I get rid of it down here because it is now represented up here. And because the keys that exist up here above the leaf level, those keys are only there for navigational reasons to help a search process find stuff. The leaves have keys, every key has to appear in a leaf because we need to make sure that if I do a range query, everything is found. Okay, now let's delete the value 187. So I go find 187. Okay, so there it is. And I delete it. Okay, great. But obviously, in the case of 187, I have to be careful that when I delete an element, I obey the density constraints. So I'm going to put a bookmark here. Q equals 3. There are 3 keys per node. Let's take a look at the density constraints. So the root must have at least 1, okay? Every internal node must have at least Q over 2. That equals... So that would be 1.5, take the ceiling, equals 2. Okay, so every leaf has to contain at least 2 elements. Every non-leaf node that isn't the root has to contain the floor of 1.5, which equals 1 element. So of course, this is easy to enforce. I don't want any empty nodes, but a node that has to contain at least 1 element if it isn't a leaf. But a leaf has to contain at least 2 elements. Now let's go take a look at this 187 problem. So let's delete the value 187. And if I delete it, I'll notice that it will likely not be a simple transformation because the node that I'm left with is only going to have 1 thing in it, and a leaf has to have at least 2 keys in it. So that means that I'm violating a density constraint. And to be clear, on an exam or assignment in this course, this is not a valid deletion. You must, the assumption is insertion or removal from a B plus tree must enforce the density constraints. So in this case, the density constraints are not enforced. And more importantly, there's a bit of other housekeeping I have to do. I have to remove that 187 from up there. But first, let's see if we can remedy what's going on in this node that's a little bit too empty. Okay, so what can I do? Well, I can't just take 370 and bring it back over here, because this node is full. I mean, I can't put 4 things in it. So it's not like the node is no longer needed. It's just that I'm going to have to go find something to keep 370 company there. And maybe it's obvious that it sounds like the best candidate would be to take 89 and just have it jump over to the right. And if I do that, then I have to make a few other modifications because, of course, now this has to turn into 89. But in this case, that's not that tough. I might have to keep modifying all the way up. In this case, I don't. But I could have to go up multiple levels. But I could just have a node move over a little bit. So in this case, I'll do that. And remember, this is a transformation that's a bit more ad hoc. You might see there are lots of ways that you could avoid having to split or merge nodes by going and looking in the neighboring nodes to find something to borrow. And in this course, therefore, we're going to take a pretty, I'm going to call it a very enlightened view to the way insertions and removals happen, which is as long as your insertion or removal is clearly doable only with local information, so using the node that you inserted or removed from and the neighboring nodes, and the density constraints and all of the other B plus tree conditions are obeyed when you're done, then your insertion or removal will be considered correct. You don't have to identically duplicate the same algorithm somebody else would have used. So an example being that suppose that I had a situation like this. So I have this node is full and this node is full. And I want you to delete something from this node. So I say delete 13. You would notice that, okay, there's the 10 can't be in a node by itself. The density constraint is not observed. You could pull in the 8 and have it join the 10, or you could pull in the 17, and that's fine. Either of those is fine with me for this course, because we're talking mostly about the applications of B plus trees. We have to show that we can use them. But in practice, database systems often take little shortcuts to avoid doing merging or splitting operations. Okay, now let's delete the value 370. So just to recap, I deleted the value 187, and in this case, the node, I was able, so this situation, when I delete 187 from this tree, I'm allowed to bring 89 over to keep 370 company, which keeps the node nice and full. That's great, and everything else is preserved. The node that I'm left with when I'm done is still obeying the density constraints, so that's fine. What if I delete the value 370? Okay, so let's go find, we go to the root, let's go find the value 370. Okay, it goes down here, it's greater than 89, goes down here. Okay, so I delete it. And again, the density constraints aren't observed. Okay, so what do I do? In this case, I can't bring 79 over. If I do that, then 63 is lonely. Then this node doesn't have enough stuff. You might notice if you were to keep pulling stuff to the right, you could eventually fill something up. That would not be acceptable. It's true that yes, you could distribute this 8 and you could push stuff all the way over, but notice that that's a linear time operation. I have to work with every single block of the tree to make that happen. And so that's not acceptable. I am allowed to pull in nodes from the neighbors, but I shouldn't be going 3 or 4 neighbors away, or even 2 neighbors away. So I try and delete 370, and now the node is too empty. And there's basically nothing I can do about that. So what do? Well, I observe in this case that because the node next door does have empty space, that's why he can't give me another node to borrow. I could just take 89 and send it back over to the left. And so what I want to do is merge these 2 nodes. There aren't enough keys available to distribute them between the 2 nodes, and that means I just have to mash the 2 nodes together into one again. So I pull the 89 over to the right, and if I do, or to the left, sorry, if I do that, then I end up with a problem happening one level above. One level above, I have 89 here, but only have 1 child pointer. So I don't need this node. And so this is no longer relevant. And actually, as a result, this whole node can be removed. So I have to recursively delete the 89 from here. And if I do that, then I end up with an empty internal node, which is a violation of the density constraints, because the density constraints say I must have at least 1 key per internal node. Okay, so now what do? Now the key here is I can't just delete the node and rearrange the pointer. That doesn't make any sense. The tree doesn't allow that. You're only allowed to modify pointers when you split or merge. You can't just wipe a node out. Instead, what I'm going to do is view this pragmatically. What I just did was I merged two nodes into one node because the two nodes together weren't full enough. Here I have a node that's definitely too empty. So why don't I just merge it with the node next door? I merge these two nodes together because they're not full enough. The two of them together have some issue, which is that the one on the right isn't full. So I merge them back together. When I merge them, I end up having to pull the 63 down, but I'm able to just delete the root. And you might notice that even if I had, and I discourage this conceptually, even if I had done something like this, where I just delete the empty node and redirect the pointer, we might observe that ultimately, like this, it still makes sense to pull this down because the total number of pointers I've got one pointer for the things less than 63, one pointer for the things greater. Well, that would be fine if I were to just move the 63 down here anyway. So one way or the other, we get to the same conclusion. I think it's better to view it more like splitting and merging at every step because that's the natural currency of a B plus tree. And of course, as we know, as usual, the deletion could keep propagating up the tree. We could go up through many, many layers. Although, if all goes well in a database system, we often have B plus trees with 1,000 or 50,000 elements per node. There usually shouldn't be very many layers. Usually a target that database systems set is to have maybe 2 or 3 layers in the B plus tree, and that's it. To have huge nodes with huge numbers of keys so that there are very few layers. Because the more layers there are, the more disk reads you have to do to get from the top of the tree down to the bottom. Now, even if we didn't have the density constraints, there's a guaranteed log n height. It's just a question of what multiple of log n. The reason we care about keeping those density constraints enforced is I/O based. We want to make sure that we do as few disk I/Os as possible. And if we know that each node could be in a separate block, that means that every node that I read could be a disk I/O. And that means that I want to minimize the number of disk IOs. I want to make sure each node is worth it, which means each node is at least half full, basically, so that I'm getting some benefit by doing that disk IO. And again, that's one reason why database systems might as well just make the number of keys in the block equal to the size of the block. If you can fit a node with 50,000 keys into a block, then just do that. Just have the entire block be taken up by one massive B plus tree node, because that reduces the total depth of the tree, and that means you do fewer disk IOs on your way down the tree. All right, let's delete 63. So I go find 63 and I wipe it out. And we might notice here, I don't think I'm violating a density constraint. So here I still have 2 elements in this node, but there is some housekeeping I have to do, which is that if I delete 63, there's a problem happening upstairs, which is that there's still a 63 up there. So I remove 63 from the leaf, and then the leaf looks like this, and then I have to propagate the new lowest value in the leaf, which is 79, up the tree. So it ends up looking like that. Now it turns out that each individual key will only actually occur in one internal node, if it occurs at all. So some keys, I don't know, 19 is one of them. Some keys never occur in an internal node, but those that do will only ever appear once, which means you only really have to walk up until you find the one occurrence of the node in an internal node and then stop. You don't. Once I've changed the 63, I'm reasonably assured that there will never be a 63 above, and so I don't have to keep going at that point. Let's delete 13. So I delete 13, okay, there it goes, and we can see that there's a problem with the density constraint. So in this case, what I'll do is, like a database system, again, we're very progressive in this course about this. I could try and merge nodes, I suppose. I could merge it to the right. You can design algorithms that are very deterministic here and would always do that. A database system typically has very flexible algorithms that try every special case because we save a lot of time. You can see that just moving one node over is not a big deal. And so in this case, we'll pull the 8 to the right. And then the node is now obeying the density constraints again. And so as I said, whether you choose to pull the 8 to the right, if you were asked to do this on an exam or something, you can choose to pull the 8 to the right, or you could choose to merge. As long as whatever you did was done properly, so if you did the merge correctly and everything was updated and all the density constraints were obeyed, or you move the 8 over and all the density constraints are still obeyed and all the updates up here are done properly, no matter which way you choose, as long as the density constraints are obeyed, you only look at something at one neighbor over. You don't try and completely rebuild the tree. Which technique you use in a particular setting is up to you. That reflects the way that database systems tend to handle this. So just to rephrase that, to be clear, you can choose if you merge or if you pull something in from a neighbor, but you can only go to one neighbor over. You couldn't, for example, walk across, in this example here, you couldn't decide to go pull something from the other end. That basically amounts to rebuilding the whole tree. A database would not do that. Let's delete 10. So if we delete 10, there we go, get rid of 10. The density constraint is not observed. Notice here, and as I've said, I will often make sure to give you trees that are as volatile as possible to make sure you can do the merging. If we look here, I can't pull in something from the neighbor. If I bring 7 over, then this node is going to be too empty. If I bring 17 over, then this node is going to be too empty. So I'm going to have a merge on my hands no matter what. Now, as I said, you can choose if you merge left or merge right, as long as the merge is correct. So I'm going to merge a node with one of its siblings. In this case, I'll merge over to the left. So I bring the 8 that I had. It goes over here. I then have to update what's happening up on the top. So here, obviously, this no longer makes any sense because the pointer I had no longer exists. So what I have to do is shift these things over, and so I actually end up with this. I just have to delete this because I can, maybe I'll draw it like this. I just delete the 8 and the pointer after it, conceptually. I just pick up this entire thing and just sort of move it over and set it down where the 8 was. And now I have a B+ tree whose structure has been restored. So now I guess we have to talk about, if we know what B+ trees are and we know how to store them, or we know how to break things up into nodes of a tree and then represent it by these B+ trees, where we, I guess, get to decide the total number of keys per node. Then the question is, well, what are good choices? And also, can we do some analysis to figure out how much work has to be done by the database if we know things like how big our keys are, and how many rows there are in the table. So how many things we might want to put into our B+ tree. And there's a few formulas here. I'm going to, in some of the live tutorials and in some of the notes I post, have embellish on this a little bit more, because it's an analysis approach, so maybe having a lot of examples on hand is helpful, but the slides are just going to go through the high-level stuff. So the first question is, what is a good number of keys per node? We've been working in these examples where we're doing with 3 keys per node because that's convenient and they fit on the slide. But actually, the B+ trees that tend to be used in database systems have a huge number of keys per node. Because remember, what they're optimizing isn't necessarily processing time. They're trying to optimize the number of disk read or disk write operations. And so essentially a database system will have some defined block size that's being used for the disk. And usually that's determined by a combination of things. It might involve some of the actual hardware that's being used. So certain disks might actually have a different natural block size. That's outside of our scope. Suppose that we know the block size. Suppose we know that blocks have size B. It turns out that it's useful to try and make each B+ tree node as big as possible such that it fits into one block. So have it fill up the entire block. And the idea is, again, we can't assume that if there are multiple nodes per block, that any particular traversal that we do, so if we have a B+ tree and we do a traversal that ends up wandering down through this sequence of nodes, how do we know whether all of these nodes will be in the same block or not? Certainly we might be lucky and they might be in the same block, but we basically have to assume, in the worst case, that all of the nodes we traverse are in different blocks. So therefore, because we really, really want to avoid reading disk, I guess our prime objective becomes, let's do anything we can to reduce the likelihood of having to go to disk just one more time. And one way of doing that is making the node as big as possible. Because the bigger the node is, the fewer nodes we're going to need. And the fewer nodes we need, the fewer disk reads we have to do. So the first question is, if we know our block size, how do we know how many nodes we can actually fit, how many keys we can actually fit into that node, if the node is the entire block in size? So this formula gets at that. So the first observation is, if we know that our blocks, let's say, have size 1,000, it's not as simple as saying, well, our blocks have size 1000 and each key has size 10, so we can fit 100 keys per block. Well, it's not that easy because the node itself consists of more than just keys, as we've seen. In these examples we've been doing where we've been working with 3 keys per node, we've got, there's, whoops, that's not B, that's C. There's C, there's B, there's A. But there's also these 4 pointers hanging off, and of course we need to store those as well. And so we have to make sure that we choose a node size that's big enough for as many keys as possible and also making room for that number plus 1 pointers. So remember that if there are n keys stored in the block, then there have to be n plus 1 pointers. So we have to know we have to have some knowledge about the actual data we're working with, and so the formula works around that. We just use variables. So suppose that the keys themselves require k bytes each, and that our blocks have size b, capital B, bytes, and that pointers require this number. So keep in mind that pointers do not necessarily mean the same thing they would for memory. So we know that when we work with pointers in something like C, in the C language, we know that a pointer is just a memory address. These are pointers that refer to disk locations. Now, they probably are addresses, but they may not have the same size. So, I mean, something like 64 bits is probably sufficient, but we shouldn't make any assumptions about that. So let's assume it requires p bytes of space. And that could be any number because obviously we could be working with a massive distributed network database or something where theoretically a pointer's, the address it refers to could be on a different machine. It could actually be a network oriented address of some kind. So in any case, we use these variables. The idea basically is we want to fit as many nodes as possible into our block. Or as many, elements as possible into our node. We want one node in our block. I keep confusing nodes and keys. So if n is the number of total keys that go into our block, or into our node, the size of the node ends up being, okay, k times n, that's the number of bytes taken up by the keys, p times n plus 1, which is the number of bytes taken up by the pointers. And what we want is for the total size of the node to be at most equal to, let's outline that properly, at most equal to the size of our block. That's it. We just want to enforce this inequality. And if we rearrange that a bit, we get that n is less than or equal to this value. So if I want to determine the maximum value n, such that a node with n keys fits inside a block of size b, what I want is this. So I take that fraction, and that could be a decimal value. That could have a fractional component, which we obviously can't have 0.3 of an element. So we take this expression and we round it down. We take the floor. And we get this. So if I have a block size, I know the size of my block, the size of a pointer, and the size of my keys, then I can determine how many elements I can fit into my block at most. And hopefully that fits in pretty evenly. There could be a little bit of leftover wasted space. So that's the first question. If I want to make my nodes as big as possible to fit into one block, I need this number of elements per node. Now the second question is, okay, suppose I know that. Suppose I know how many elements I have per node in the B plus tree. The next question is, if I know that I have, let's say, 1 billion items in my table that I'm indexing. So a billion keys go into my B plus tree. The question is, how many disk IOs can I expect to do if I'm searching for one row in the table? That's the next question I want to be able to answer. And to answer that, I have to know how many levels there are in my B plus tree. So I've gotten to the point now where I know that my B plus tree, let's start with this example. If my B plus tree uses only one node, a node fits into an entire block, then I'm guaranteed that every single node that I load is one disk IO. And so that means that and so then here's the leaf level down here. That means if I want a particular row from the table, what I would probably do is, and then we've got something like this happening where there's a pointer to a piece of data. If I want a particular row from my table, I would start at the root, I would go in and I would traverse down the B plus tree, and each time I see a node, that's one disk access. And then I finally get down here, and the pointer at the very bottom tells me where on the disk I can get the row I'm looking for. So there's one access, one access, one access, one access, and then I guess an access to actually go and grab the row from the table. If I need the row. So at this point, because we know that each node fits exactly into a block, there's never going to be a case where I happen to already have the block I want. Each node that I load is definitely one disk I/O. So I want to ask the question, if I know how big the nodes are, how many will I need to load to get to a row? Basically, how deep is the B plus tree? And before I get there, I want to make another observation, which is, suppose I'm asking the question, as I might have done in 225, how many nodes are there on a particular level of a complete binary tree? So just to observe, notice that if I want to count, let's say how many things, here's level 0, here's level 1, here's level 2. How many things are there at level 2 of this tree? Okay, well, the answer turns out to be 2 to the 2, which is 4. But notice how you could also compute that by figuring out how many child pointers the level above has. And then there's the next question is, okay, so what happens if the tree, let's say, is 3 children per node, but is still as complete as possible? So there are 9 nodes at this level. How many nodes are at the next level, assuming that there are as many as possible? And the answer is, well, each of these 9 nodes will have 3 child pointers. And so that means that the number of nodes down there would have to be this number, 9 times 3, which is 27. So that's just note that that's the piece of logic that I'm using. And I can, on the next slide, and I will use that logic recursively. If I want to know, if I know that there are 3 things at this level, and I want to know how many things are at the next level, then I would say, well, it's the number of things at this level times the number of child pointers there are at this level. In fact, I could actually take that further and I could say, look, I know there's 1 thing at level 0. How many things are there at level 1? Well, there's the number of things at level 0, so that's L0, times the number of child pointers at L0, which is always the number of nodes times 3. So this means this number here is the number of nodes at level 1. How many nodes are at level 2? Well, it's this number times 3. So that's the number of nodes at level 2. And you might notice that what we're really computing here is just 3 to the power of whatever level we're going to. If we're going to level 0, we do 3 to the 0. If we're doing level 1, we do 3 to the 1. The reason why I'm trying to lay it out in terms of child pointers is that unlike a typical binary tree or a ternary tree, B plus trees have this odd property where the leaf nodes have a different structure than the internal nodes. So the formula we use can't be as straightforward. So here's what I want to compute. If I know how many elements I have in my tree in total, elements, not nodes, if I know how many elements I have in my tree, how many keys, and I know how big each node is, how many keys there are per node, how many levels are there in the tree, the way I have to derive this formula is sort of backwards. What I'm going to do instead is I'm going to derive the depth of the tree, or sorry, I'm going to derive the number of nodes, the maximum number of nodes that can be in a tree of a particular depth. So I'm going to work backwards and then solve it. We can preview the next slide. Here's what I want. If I have a tree with if I have a tree with this number of nodes and this n is the number of elements per node, then there's this formula I can eventually use that tells me that the number of levels in the tree is at most this whole thing. But I just want to walk through how we derive that. So first, if I have a tree that I know has this number of levels, and that includes the root nodes. So just to be clear, this tree here, this binary tree, has 3 levels. And we number them 0, 1, and 2, but there are 3 of them. Okay, so I have a tree with L levels. And the question is, how many elements can this contain? And keep in mind that there's sort of the best case, worst case thing. In the best case, I guess for a database at least, in the best case, the tree is really, really full. So there's a huge number of nodes, small number of levels. But we don't want to think about that. We want to think about the worst case. In the worst case, the tree has 3 levels. And we know that in a binary tree, we can have a tree that has 3 levels that has 3 elements. We obviously don't want that. That's why we had those density constraints. So what I want to compute is, if I have a tree with 3 levels, what is the absolute minimum number of nodes that can be in, or number of elements that can be in that tree? So if the tree is as empty as it's allowed to be by the density constraints, what is the minimum number of things it still has to contain if it has L levels? And this is implicitly assuming that L is not 1. So like we won't worry so much about what happens if the tree only has 1 node, if it's just the root. Let's assume the tree has got at least 2 levels, or probably more. So every internal node, everything that isn't a leaf, has to have this number of keys in it. So it has to have, that's the density constraint we stated earlier. And if it has this number of keys, then it has to have this number of child pointers. So I mean, for example, in a binary tree, you've got 1 key and 2 child pointers. In that 2-3 tree, in the case where you have 2 keys, you have 3 child pointers. So I know that every internal node has to have this number of child pointers. And as I said a minute ago, we can use that to figure out how many nodes there are in the whole tree, because we could say, well, we know that there's 1 node at level 0, and then how many nodes are there at minimum at level 1? Well, there has to be, the minimum number of child pointers I can be using at level 0 is this number. So it has to be at least this number of nodes at level 1. How many nodes at level 2? Well, here's the number of nodes at level 1, multiply that by the minimum number of child pointers per node, and we get this. So we can compute the minimum number of nodes that have to exist at each level of the tree using that logic. Now, when we get down to the last level before the leaves, there's also the problem that the leaves contain slightly more keys than the internal nodes because of that issue. Well, for one thing, that every key has to appear in a leaf somewhere. So we have to change the formula a bit. It's not as easy as saying the total number of nodes in the tree is just this to the power of L. We have to take it apart a bit because we have to count the number of things up to level L-1 and then add a special term for the case of level L itself. So we can therefore determine the total number of elements in the tree. It's just this formula which has been expanded out. There's the first L-1 levels, and there's the bottom level. And so the total number of elements is in the tree, which is T, is at least equal to that number. In the worst case, if the tree is as empty as possible, the total number of elements still has to be at least this value. Now as I said, we tend not to care as much about that. If I know the B plus tree has 3 levels, I don't care as much about the number of elements. The reason I derived it this way is we eventually want to figure out, if I know the number of elements, what is the maximum number of levels that I have to have? And it turns out, I'm not going to derive this part of it. You can use your imagination. Using some logs in algebra, I end up with this expansion. So the number of levels is at most, so in the worst case, when the tree is as tall as possible, if I know how many keys, so this number of keys, and this number of keys per node, the total number of levels is at most this whole expansion here. So let's use that for a quick example. As I said, I'll post some notes that do a few more of these. Suppose we have a B plus tree with this arbitrary number of total keys, and we know that each disk block is this bizarre number of bytes in size. Pointers require 10 bytes, and keys require each 7. Now, interestingly, it points out there's a little optimization that we might do, and you'll see in the questions I post that something similar happens. We know that we can't store everything in memory. We don't have enough space. However, the database does, each block is what? 10,000 bytes. We could probably store a few blocks in memory. Now, unless you're specifically told that blocks are stored in memory, do not assume you are allowed to keep them there. So even if the memory is massive and blocks are 10K, unless it says to keep something in memory, don't. But here it points out, hey, if we're going to use this tree all the time, it makes sense we keep the root node in memory. We can't keep every node in memory, but if we're going to keep something in memory, let's keep the root, because we're going to need the root over and over again. So assuming that the root node can be accessed for free with 0 I/O operations, because it's kept in memory, what is the maximum number I can expect to use if I'm locating one thing inside this B plus tree? So what I'm really asking is, what is the maximum length of a I'm not going to draw it. What's the maximum length of a traversal in the tree under the worst case assumptions? So the first thing I do is I work out how many nodes, how many elements are there per block. So this is actually this is a keys per node and per block, because a node and a block at this point are essentially the same thing. So that's not nodes per block. I'll fix that before I post it. So we notice that if we evaluate the formula, the number of keys per node is apparently this. So we have to round down. We can't use more than one block for a node. That wouldn't make any sense in this context. So we have to use 623, which means we waste a little bit of space at the end. So there are 623 keys per node. And that means that the density constraints tell me that every internal node has to have this number of keys, and every leaf has to have this number of keys. Okay, so then we can work out how many levels there are in the tree. which is, we know that n is 623, so we compute this formula. I'm not going to belabor it. We can plug things into formulas by now. So we do that, and we get the number 3. And that means in the worst case, the tree has 3 levels. So that means if I have to traverse the tree, to locate a node, I have to walk through 3 different nodes, or to locate a particular key at the lowest level of the tree, I have to walk through 3 different nodes, which are 3 different blocks. But it points out that because the root is already in memory, only 2 of those are actually disk I/O operations. Now, just to close that out, I will post some notes with a lot of applied exercises on working with those formulas and reasoning based on them. I've got another example coming up where I talk about why we would care about these numbers beyond just computing the number of levels. And the live tutorials will contain some more exercises on that. That's one of the things that's just better to do that interactively. So we've spent all this time doing this. What was the point? How does this factor back into a database? We've seen that certainly these are good structures for searching things, but how does it factor into the databases we've been working with? And the answer is, ideally, if I run a query, if I say select star from observations, where, and then I give some criteria, ideally the database should go and figure that out. I, the database programmer, shouldn't have to tell it to use any particular data structure. And it turns out that I don't. So I do not have to tell the database to go use a B+ tree when I'm running a query. However, I do, when I create the database, have to give the database some hints as to what to create B+ trees for. And that's what's called an index in SQL. And I guess I'm saying B+ tree, which is often used, but there's no reason a DBMS has to use a B+ tree. It could use all sorts of other data structures as well. It could use hash tables. It could use regular binary search trees. It might use a hash table. I don't think it'll use a regular binary search tree. So what you use is this directive create index. By default, a database system will typically create an index for you, index meaning B+ tree or something, for a primary key. But you're allowed to create as many indices as you want on a table. And when you create an index, the database prepares a B+ tree or something similar for the table based on the key columns you give it, which don't actually have to be the keys of the table. If you know that you're going to be doing a lot of searching on a particular criteria, so for example, I'm going to do a lot of searches by station ID, I could create an index called station index. Just like with constraints, the name is just for your own purposes so you can delete it later. On my observations table, and then I'd give the columns to use as the keys. So I'd say, okay, how about station ID? And then it would go, and it might take a minute if I ran it on an existing database, and construct a B+ tree, and the B+ tree in its lowest level would contain these pointers which point to, so somewhere on disk is my actual table, and there are all of its rows. The lowest level of the B+ tree, these data pointers would point me at specific rows of the table in whatever order they're in. And I'll talk about the ordering in a minute. And so if I traverse the tree, I can locate rows that have specific values. And of course, these would be, if I use an index on station ID, these values would refer to station IDs. So, and we go back over here. So I could do that. Now, the reason why I have to do that myself, the database does not do that automatically because, of course, when I create the table, how does it know what I'm going to be searching on a lot? And, of course, there's also the matter that the B+ tree does take up space. So it only wants to create indices for things that I think are worth it, for the space and for the time it takes to keep those indices current. Because when I insert values, I have to update the index, update the B+ tree. So I have to create my own indices. And all along, it turns out, on assignments 3 and 4, on the queries you were writing, on the databases we used, VWSN, IMDb, and the Fairies ones, I defined a whole bunch of these extra indices on things like station ID and temperature and sailing dates and whatever, because I knew in advance you'd be writing a lot of queries and I wanted them to be fast. So you do have to do a bit of legwork at the beginning to configure the database to have certain fields be easily searchable, or else it might just use linear search for them. That said, once the index is set up, you don't have to do anything to use it. So if I have an index on station ID up here, and I write a query where I say station ID equals 6, the database should see that and know, hey, station ID equals 6 sounds like a good use for this index. I, the person writing the query, does not have to know about the index or tell the database to use it. That should be automatic. So an index itself is an extra data structure. The table is stored separately from the index in many cases. There is a case where they're linked, and I'll show that in a minute. But the reason why that's helpful is I can make as many indices as I want. So conceptually, I have a table here. So here's my table. And there are all of its rows, and they're stored in whatever order. And then over here, I'm going to draw it sideways. Over here, I have a B plus tree, and then there it's the leaf nodes, and then up here it's other nodes. And then this goes down here somewhere, and then this, and then there's the root. So there's my B plus tree, and then the lowest level of this contains all these pointers that point to specific rows. And so this one, for example, this one goes to this row, this one goes to this row, these ones go down here. Okay, and then I've got an index on some particular thing, like temperature or station ID. And if I wanted, I could define a second index completely independent from the first one, and then this is a B plus tree just like before. And then there's that. And then its pointers point somewhere else, and it's completely arbitrary. So I can have as many indices as I want, and they're all independent. And that, of course, means if I go and create a lot of them, I'm going to use up a bunch of extra space, and I'm going to require a bit more time to do insertions and updates, because we have to keep all of these B plus trees updated and synchronized to the table. But creating an index in general doesn't require, there's no reason an index monopolizes a table. It's also true that by default, the database will normally, whenever you define a primary key, automatically define an index on that. So there's no need to define an index on a primary key in a table. And we'll see in a minute that the primary key index is usually a special kind of index as well. So I can make as many indices as I want. We'll come back at the end to talk about an interesting implication of that, where I can actually use indices instead of looking at the table in some cases to answer basic questions. It's worth considering that it's worth considering. This is after 3 months, I'm amazed that most of my words are still English. I don't know what considering means. I'll see if I can think of a definition. But in the meantime, it's worth considering that in this example, the table was just a bunch of rows apparently in an arbitrary order, and the indices were just pointing all over the place, which is great because it means I can have as many indices as I want and they can all be independent. But I am still allowed to sort the table, right? I mean, just like at the beginning, I was thinking about sorting the table by some value and then using binary search. I'm still allowed to do that. But of course, I can only do it by one particular thing. If I choose to have one value be special and keep the table in sorted order by that value, it can be the only such thing. I can't keep the table in sorted order by two different values. And so I want to show some diagrams. Because we have to talk in an abstract sense here, I'm going to use a very basic conceptual notation for them. So let's assume that I've defined an index over some key values. So this index is defined over year, month, and day together. And this index is defined over the value temperature. Let's assume that we've defined an index and these symbols, K1 to Kn, refer to the values being indexed. Who cares what they are, temperature, year, month, day, whatever. They're just some set of the collection of keys I'm using in the index. And also remember that the word key in this lecture means an element of a B plus tree. Not necessarily, it could be, but not necessarily a primary key or a foreign key in the table, because this is, for example, not a key in this table. So what I end up with is similar to my sketched out diagram from a few slides ago. What I end up with is sort of this, much crisper typeset version of that diagram. My index structure may not be a physical array, but it's some kind of structure that functions that way. I look up a key, like K2, and it tells me where to go on disk to get the row that corresponds to K2. Right? So the index itself, we'll just draw it as this vertical array, but really it could be, again, a B plus tree or a hash table or whatever else we think is convenient to search. So an index is called a primary index or a clustering index, and as you may know, I'm a big fan of descriptive names. Why should we call it a primary? Let's call it a clustering index to describe what it is, as opposed to where it fits in the hierarchy. A clustering index dictates the order of the underlying table. So when you have a clustering index, you still have an index structure, but the table is required to be sorted by that index. In other words, if you have two keys and K1 is less than K4, K1 has to appear before K4 in the actual representation of the table on disk. We call this a primary index because this is a special kind of index. You can only have one such index for each table because you can't keep the table sorted with respect to multiple criteria at once. So normally we actually use the primary index, the clustering index, for the primary key of the table. Because if something's supposed to be special, we assume the primary key has significance. We've chosen it based on properties that give it significance. Uniqueness, the fact that it defines the data of the table. It makes sense we should expect to do lots of searches by the primary key. And that's one of the reasons why choosing a good primary key is important, because it can optimize operations like joins, where you'd often be using an index structure. So when you have a primary index, a clustering index, the table has to be maintained in sorted order with respect to that index. This is an example here, this thing, of what's called a dense index, which is to say, if I have a bunch of rows and each row has some value, a key, so maybe temperature, maybe station ID, every single row is pointed to by something in the index, which means the index is keeping a duplicate copy of every single key in the table, which of course requires some maintenance, but it also means the index is big, because there has to be one key in the index for every single row in the table. It does mean that if you tell me, if I get to a specific location in the index, I have a direct pointer to that exact row in the table. And it also means, as the slide is pointing out, that basic existence questions, like, is there a record in the observations table for temperature 6.1? That question can be answered without ever actually looking at the table. I just ask, is there a position in the index for that? Does that key appear in my B+ tree? If the answer is yes, then the answer is yes. Then it is in the table. If I want the row, I have to go to the table. But I can actually answer basic questions about whether the row exists just by looking at the index. Now, the alternative is what's called a sparse index. And I want to, I guess I'm going to annotate this a bit. So what we might have is the table is split among multiple blocks. So there's block 0, and this is block 1, and this is block 2. And so the idea is, if the table is stored in sorted order, then you don't need as much information in your index because you can use binary search. For example, if I know that K0 is here and K4 is here, and I'm looking for a row for K2, it has to be in the middle, it has to be between. I could use binary search between these two values to find it. So I don't need every key to be stored in the index if I know the table is in sorted order. So typically what we do in that case, we can define what's called a sparse index, which is a much more compact index structure, which is nice, where the index only contains the keys for the first row in each block, with the understanding that the block is sorted. So if I know that the first row for block 1 is K4 and the first row for block 0 is K0, then I know that K2 or K3 must be in block 0 if they exist. So I just load block 0, and once I load block 0, I'm not worrying about the disk anymore. I can do linear search in block 0 for all I care. I found the block quickly. There could have been billions of different blocks, and I found the one that is supposed to contain the thing I'm looking for. And then once I load it, who cares what I do? Although I could use binary search. I probably would. But at that point, it's no longer a disk I/O problem. The issue is that a sparse index has to be defined on a clustering index, because if the table isn't sorted with respect to the index, you can't use a sparse index because you don't have that assurance. And so, yeah, this is pointing out that there's actually no real disadvantage of using a sparse index here. The dense index takes up lots of space, and ultimately we still end up. So think about it. If I use the same breakdown of blocks, where this was block 0, the dense index is way bigger, and that means I might have to load a lot more blocks before I know that K2 is in block 0. So I might actually do more work with the dense index than with the sparse index, because I have to traverse the index, then load block 0. And then once I've loaded it, it's no longer a disk I/O problem. Here, I traverse the index, I figure out that K4 is block 1, K0 is block 0, which means K2 must be in block 0, and then I load block 0, just like I did before. I might actually save time, if I'm lucky, and I can define a sparse index, which I can only do if it's a clustering index. Then there's this idea, so of course we are allowed to define as many indices as we want, but only one of them can be the primary index. Maybe none of them are, but only one of them can be. Only one of them can be a clustering index. So if I have multiple indices, some of them are going to be non-clustering. And what we have there is, we have our index structure, which of course we traverse it somehow, and we find out that K1 goes with this row. But the rows themselves that are stored on disk aren't ordered in any way. So K1 might end up, for example, if the table's primary index is on station ID, but I want to search by date or by temperature, then of course the row I'm looking for, if two rows that have a similar temperature, might be really far apart in the table because the table is sorted based on something else. So a secondary index is non-clustering. There's no underlying order of the table dictated by a non-clustering index, which means I can have as many non-clustering indices as I want. They're each just separate indices full of pointers that point to arbitrary things in the table. I can still do efficient lookups and maybe efficient range queries, but if I do a range query, I don't get the benefit I would get on a clustering index. So both forms of clustering index, if I ask you, so if I know that the assumption we started with was that K, the keys are already ordered somehow. So K1 is less than K2, K2 is less than K3. Suppose I ask you to compute a range query and give me every key between K1 and K4. You might notice all you have to do is figure out where K1 is and then just walk down the table. You don't need to look at the index ever again. You look at you find K1 in the index, walk down the table until you hit K4 because you know the table is sorted. The same is true with a sparse index. I find K1, okay, so it's between K0 and K4. I do binary search, I find it there, and then I just walk down the table. And so there's lots of rows in the same, and the rows will actually also be very compact. I'll end up loading very few blocks for my range query. So I can do a range query with a dense or sparse clustering index really conveniently. I can still do a range query with a secondary index. The problem is it might require more work, and I certainly have to use the index more. So suppose I want everything between K1 and K4. Well, what I would do is I'd find K1 in the index, and then I'd go load the row. And so, I don't know, I take one block I/O to get the index, or 2 or 5 or 10 or whatever, however big the B plus tree is. And then I say, okay, so let's load K4. I have to go load a block for, or K1. Let's load K1. That's down here. Okay, now what's the next thing? Well, let's look at K2. So I go in the index, I jump to the next element, I load K2. That might be from a completely different block. I can still find all the rows in the range, but actually loading them can be pretty unpleasant. I have an example of that in a minute. Now notice that if you have a secondary index, it can't be sparse because the order of the items in the table is arbitrary with respect to the secondary index. And so I don't have the same assurance I have back here where I don't need K1, 2, and 3 to be in this index because I know that they're between K0 and K4. I don't have that in a secondary index, so I have to have a dense index if it's a secondary index. Let's take a look at this. This is a more concrete example. So suppose I've decided to define a secondary non-clustering index on my observations table. I've used station ID as my key. And for whatever reason, just for the sake of the example, there's only 2 rows that fit in each block. So here's block 0, here's block 1, here's block 2, and here's block 3. And remember that in a table like this, there could be 1,000 rows per block, but there could still be 1 billion blocks. Now suppose also that the index is so compact and clever that the entire index structure, the whole B tree, somehow fits inside of one disk block. So using the index only ever requires one I/O operation. That's not realistic, but it's to try and clean up the example. First question, how many block I/O operations do I need to search for and retrieve the row with station ID 7? So here's how I would map that out. First, I would use the index. I would load the index, and that would take 1 I/O because it says it takes 1 disk block for the whole index. I load the index, I search it. Once I load it in, who cares what I have to do because there's no disk operations? I find row 7. I follow the pointer, and I load block 1. So that sounds to me like 2 disk I/O operations. So 1 block read to read the index, 1 block read to find row number 7. Okay, so 2 disk I/Os in total. Ooh, there's another one of those. Okay, we gotta start closing more parens here. How many block I/O? Here's an interesting question. How many block I/O operations are needed just to count the number of rows in this range query? So this range query is saying, I want to know all the stations between station ID 4 and 10. Find me all the rows with a station ID between 4 and 10. Now, what you'll notice here is all I'm doing is counting them. I don't need to know anything about the row besides that it exists. So what I could do is I could load the index and just figure out how many. It's a dense index. It has to be because it's a secondary index. I load the index. I just count how many things in the index have the station ID in that range. And I just ignore the table. I never load anything. So that can be done in one block read operation because the answer can be computed with just the index. Now, in the questions we'll see later, obviously we don't typically have the index fit inside one disk block. But even if the index was 10 disk blocks, reading the entire index is usually better than reading a huge table. Except in this case. How many block I/O operations are required to retrieve all rows with this range query? Retrieve the rows, actually go and read the blocks off disk. Well, let's think about this. Suppose you'd never heard of an index before. Let's just really go to town on that. It's not there. There's no index. Suppose you've never heard of an index. How many disk I/O operations would it take you to get me all the rows with a station ID between 4 and 10? I don't care what order they show up. Just give me all of those rows. What you'd probably do is you'd read block 0. You'd look at every row and you'd say, this one. Read block 1. Okay, this one. Read block 2. Okay, this one. Read block 3. Okay, that one. You read 4 blocks. You just went through the entire table in order and did basically linear search. And that would take you 4 block I/O operations. Okay, 4 block reads. Okay, so that's the baseline example with no index. What happens if we make the mistake, and you'll see why it's a mistake, of using the index here? Okay, so if I perform the result using the index, how long does it take? Okay, so 1 for the index, 1 block read just to get the index into memory. Keeping in mind, this index is magical and only takes up 1 block. In reality, you can expect the index will take up more than 1 block, and you'll need to do more than 1 block read to get it into memory. So I read the index in 1 block. Then I go grab this row here, and that requires me to read block 3. So there's block 3. And then I go read the row 5, and that requires me to read block 2. Whoops, not there. And then I go read 7, and that requires me to read block 1. And then I go read the 10, and that requires block 0. For a total of 5 block reads. The index was really helpful in looking up a single row. But it wasn't very helpful in doing this range query because I had to jump all over the place. If it happened that my index was a primary index, then all of the rows I need would be next to each other. So and actually even then doing linear search on the table wouldn't necessarily hurt that much because I could ignore certain blocks. But in this case, the indexes actually hurt me. Doing the range query with the index is actually worse than just using linear search because the index requires me to walk all over the place. It can actually get even stranger because imagine what would have happened if I ask, let's clear this, what would happen if I say, can you give me all of the rows whose station ID is between 4 and 16. So remember that if you do this with linear search, it takes 4 block IOs. You just read all 4 blocks and just ask all of them in order. That's it. So it's all, at most, the worst case time if you do use the simple algorithm is always just going to be linear search, the size of the table. What if I use the index? Here is the sequence of loads I'm going to do. I'm going to load the index itself. We'll call that I. Now I'm going to go down and I'm going to load block 3. Now I'm going to go down and I'm going to load block 2. I guess I have to unify my notation. I load block 2, okay? And now I'm going to go and load block 1. Now, assuming this table has 1,000,000 blocks, I could end up loading all 1,000,000 blocks. That's not the only problem, though. Okay, then I go load block 0. And now I go load block 1. And you might be saying, oh, but you already have block 1 in memory, don't you? Okay, maybe. It's a coincidence. But what if I wanted to load block 3 again? And so let's see, then I go load, there's block 1 again, and then I go load block 2. Yeah, maybe I still have one of those blocks in memory, but if this table had 1,000,000 things in it, I could load block 0, block 1, block 2, block 3, up to block 1,000,000, and then load block 0, block 1, block 2, block 3, up to block 1,000,000 again. If I'm not careful, the index can actually take longer. It can take a huge amount longer than just doing linear search. If each block has 100 rows in it, and my query is supposed to return, 50 of the rows in each block, if I'm not careful, I could load each block from disk 50 times to service the query using the index. And that's not to mention the time it would take to use the index. So this is one of the reasons why there's a lot of nuance involved in the way databases work, because when the database sees your query, it has to make an informed decision. Should I use the index for this or not? An example where maybe you should use the index, a range query where you maybe should use it is, what if you're only doing a range query of 2 things? A database might think on balance of probabilities, you're probably going to need, I don't know, at most 2 blocks for that. And the table has 4 blocks. You might get some savings there. And if the table has 1,000,000 blocks and you're looking for a range that might only contain 10 things, maybe it's better to use the index. But there comes a point if you expect to get a huge number of hits on your range query where it's actually faster to not use the index at all because of the overhead of having to constantly go back to disk. So one last thing, and then I'll also post some notes about comparative analysis of using indices, whether they're sparse or dense, and how many keys go into a block as a set of notes, and we'll talk about those in a tutorial session. One thing I want to observe here, suppose I'm doing a query where I say, give me every or actually no, don't give it, just count. Tell me how many observations in the data set come from February 1st, 2017, and have a temperature between 0 degrees Celsius and 1. And we'll notice that I have an index on temperature and I have an index on date. And if I just asked you, could you tell me how many observations there were for this day, you would be able to do it, just like in this earlier example, you would be able to do it, I had it here somewhere, here we go. You would be able to do, just like you could do this without using the table, just using the index, you would be able to compute the number of observations for a particular date just using the date index. And you would be able to compute the number of observations for a particular temperature just using the temperature index. So what I want you to think about is, what's stopping you from what's stopping the database from computing all the dates that match the query here without using the table, just using the index, and then over on the other side, computing all the temperatures that match the query here without using the table, just using the index, and then taking the intersection of the two internally. It might be able to actually evaluate this entire query without ever looking at one row of the real table, only analyzing the metadata of the indices, because all that's being requested is the count, the number of observations with that property. It turns out we could go further. You could actually compute the sum of the temperatures, or the average temperature, because those are all stored in the temperature index. And so it's a case going back to that query at the very beginning. Should we do it with a where clause or an intersection? Where what the database actually does very well could be an intersection by the time it's done. And it depends, what decision to make depends on the different facets of how it's representing that data. So we'll talk about that again. We'll talk about some examples of that in one of the tutorials. And I'll post some notes about that so you can work through it. There will be questions on the assignment and exam that amount to, is it better to use a sparse or dense index for this task? Is it better to use the index or just to process the table with linear search, or to, for example, sort the blocks of the table using that merge sort from the theorem earlier and then run through the result of that?